Good morning all. Today we are going to handle the topic armature design in DC machines. Armature design mainly consists of two topics. One is choice of armature winding and the other one is number of armature slots. We are going to see each one of them in detail. We will start with the choice of armature winding. As you have studied in your previous semester's electrical machines course, in a DC machine there are two types of armature winding. One is lap winding and the other one is wave winding. Both this lap winding and wave winding differ in the way by which this coil ends are connected to the commutator segment and by the number of parallel paths or the circuits which is existing between the positive and negative brush terminals. The diagrams of both lap winding and wave winding are depicted here. You are quite familiar with the distinguishing features of lap winding and wave winding. In the case of lap winding, the number of parallel paths will be same as that of the number of poles. Here we are indicating the number of parallel paths as small a. Whereas in the case of wave winding, the number of parallel paths always remains to be 2. Current flowing through each conductor is same as that of the current which is flowing through each parallel path. In the case of lap winding, number of parallel paths is same as that of the number of poles. Therefore, the current which is flowing through the conductor is indicated as IA divided by P. Similarly, in the case of wave winding, current flowing through the conductor can be represented as IA divided by 2. From Ohm's law, we very well know that I is equal to V by R and the relation for resistance is R is equal to rho L by A. So if we make that substitution of R is equal to rho L by A in the relation I is equal to V by R, we will be able to obtain that current which is flowing through the conductor is directly proportional to its cross-sectional area. Consider the cross-sectional area of conductor in lap winding is A1, whereas cross-sectional area of conductor in wave winding is A2. So from the standard relation, it's very clear that A1 is directly proportional to IA by P, whereas A2 is directly proportional to IA by 2. If we are making the division A1 divided by A2, we will be able to get A1 by A2 as 2 by P. That is, A1 is equal to 2 by P times that of A2, which can be said as cross-section area of conductor in lap winding is 2 by P times the cross-section area in wave winding. Now let's see the required number of conductors in lap winding and wave winding. All of you are quite familiar with the standard relation for induced EMF in the case of a generator and back EMF in the case of a DC motor. That is the standard relation of induced EMF and back EMF in DC generator as well as in DC motor is E is equal to 5 Z by 60A. So from there we will be able to write Z is equal to 60E divided by 5Pn into small a, where small a is actually indicating the number of parallel paths, E is induced EMF or back EMF. It depends upon the machine. If it is in the case of generator, this value of E will be induced EMF, whereas in the case of a DC motor, the value of E will be back EMF. N is indicating the speed, P is representing the number of poles, phi is indicating the flux per pole. So from this standard relation, we will be able to write the relation for Z in the case of lap winding by making the substitution A is equal to P. Similarly, in the case of wave winding, we will be able to obtain the value of number of conductors which are actually present is by making the substitution of A as 2. From these two relations, it's very clear that the number of conductors in lap winding is P by 2 times that of the number of conductors in wave winding. That is also mentioned here. So it's very clear that comparing with that of the wave winding, the number of conductors which are present in the lap winding is larger. As this lap winding is having large number of conductors comparing with that of the wave winding, the area required for the insulation also will be large. Therefore, the slot area will become definitely large. In the case of lap winding, it is easier to make short pitched coils, which further results in the reduction of overhang. This leads to a large saving in the amount of copper which is required for the winding. The concept of overhang has been very clearly explained in the previous video session. Wave windings are usually used in machines which are having applications of high voltage and low current applications. Low current means the current rating has to be always less than 400 ampere, whereas lap winding is generally used for applications involving low voltage and high current applications. That is, the lap winding machines or lap winding in machines can be used for applications involving current rating greater than that of 400 ampere. You must remember this rating, that is, when the current rating is less than 400 ampere we will be using wave winding, whereas when the current rating is greater than 400 ampere we will be using lap winding. So it's very clear that for small current applications wave windings are used, and for large current applications lap windings are used. The selection of number of coils and the number of turns per coil is decided by the factor that the voltage between the adjacent commutator segments should not cross the value of 30 volt. If the voltage between the adjacent commutator segments is exceeding the value of 30 volt, then definitely there is a possibility for flashover to occur between the adjacent commutator segments. So it must be taken care of that the maximum voltage between the adjacent commutator segments should not cross the value of 30 volt. Next we will determine the relation for maximum voltage existing between the adjacent commutator segments. First we will obtain the relation for EC, which is actually the average voltage existing between the adjacent commutator segments at no load condition. The relation for EC can be obtained by multiplying the number of conductors between adjacent commutator segments, that is ZC, and voltage per conductor at no load condition, which is EZ. The relation for EZ can be very easily obtained by using the standard substitution BLV sin theta. Since the conductor is placed at perpendicular to the direction of flux, therefore the value of sin theta will be 1. So instead of EZ we can make the substitution of B average L into VA. ZC is actually the number of conductors which are actually present between the adjacent commutator segments. The relation for ZC can be easily obtained by 2 TC/NC, where TC is indicating the turns per coil and NC is actually the number of coils between the adjacent segments. If it was a single coil existing between the adjacent commutator segment, then definitely the relation for ZC will be 2T. Since there are multiple coils which are being present between the adjacent segments, in order to obtain the value of ZC we have to multiply 2TC with NC also. So this gives the average value of voltage existing between the adjacent commutator segments under no load condition. Next we have to obtain the relation for maximum voltage between adjacent commutator segments at loaded condition. We can easily obtain the relation for maximum voltage between adjacent commutator segments at no load by simply making the substitution of BG here, where BG is actually the maximum flux density under no load condition. So if you are making this substitution of B average with BG, then the value which you will be getting will be the maximum voltage between adjacent commutator segments under no load condition. But in actual practice what we require is the maximum voltage between adjacent commutator segments under loaded condition. So under loaded condition the value of maximum flux density is indicated as BGM, and this BGM is actually 1.3 times the value of maximum flux density under no load condition. That is, BGM is equal to 1.3 times BG. So in this relation, instead of BGM we can make the substitution of 1.3 times BG. If we know the values of B average and KF, KF is actually field form factor. It is actually the ratio of B average to BG. So if we know the values of B average and KF, then definitely by dividing B average with KF we will be able to get the value of BG. Thereafter, making the standard substitution of KF as 0.66 or 0.67, we will be able to get this relation in a simplified form 3.88 TC NC B average L into VA. This can be approximated as 4. Therefore, the relation can be written as 4 TC NC B average L into VA. The value of TC is actually turns per coil. The total number of turns can be easily determined by dividing the total number of conductors by 2. That gives us the total number of turns which are present in the armature winding. If we want to determine the turns per coil, we have to divide the total number of turns we have to divide the total number of turns with the total number of coils. C is indicating the total number of armature coils. So making the substitution of TC as Z by 2C, and B average is actually the specific magnetic loading, so making that substitution P5 divided by pi dl, and VA is actually indicating the peripheral velocity, and you very well know the relation for peripheral velocity as pi d n by 60. Making the suitable substitutions and simplifying it further, we will be able to obtain the final relation as 4 into Nc divided by 2C into phi Pn Z divided by 60. Please don't confuse between Nc and C. C is indicating the number of armature coil, that is the total number of armature coils which are present in the machine, where Nc is indicating the number of armature coils which are present between the adjacent commutator segments. So finally we have obtained the relation for maximum value of voltage which is existing between the adjacent commutator segments as 4Nc divided by 2C into phi Z and P by 60. Instead of this, we can make the substitution as EA. E is actually the relation for induced DMF or back EMF, which is actually phi Pn Z by 60A. Since A is not there, so definitely we can make the substitution for this particular term as E into small a, where small a is indicating the total number of parallel paths which are present in the machine. From this we can obtain the relation for C, which is actually the total number of coils which are present in the armature winding, as C is equal to E small a Nc divided by 15, whereas Nc is actually indicating the total number of coils which are present between the adjacent commutator segments. The standard relation for Nc is P by A. In the case of lap winding, the value of A is equal to P. Therefore, the value of Nc is 1. While making the substitution for Nc is equal to 1 in this relation, we will be able to get the value of C for lap winding machine as Ep by 15. Whereas in the case of wave winding, the value of A is 2. Therefore, by making the substitution in the standard relation for Nc, which is actually P by A, so the value of A is 2, so we can get the value of Nc as P by 2, and making the substitution in this relation, we will be able to get the value of C is equal to Ep by 15. So for both the cases of lap winding and wave winding, the minimum number of coils which are present in the machine is given by the standard relation C is equal to Ep by 15. The factor which leads to such a conclusion is that the maximum voltage which is existing between the adjacent commutator segments should not cross the value of 30 volt. So far we have seen the choice of number of armature coils. Next we are going to see the selection of number of armature slots. In this, first we will start with the factors which are affecting the selection of number of armature slots. The first factor is slot pitch. As all of you know that the slot pitch is defined as the center to center distance between the adjacent slots. If you are choosing a machine with a very large number of slots, then definitely it will result in a value of smaller slot pitch. This further leads to the condition of small tooth width. Generally, it is difficult to have such a construction with smaller tooth width. So that is one of the problem if we are choosing a very large number of slots. The second factor which is taken into consideration is the cooling of armature conductors. If the number of slots in the machine is very large, then definitely this armature conductors can be easily accommodated into this large number of slots. So definitely the bunching of the conductors in slots are reduced. That is actually the number of conductors per slots will be small if the number of slots are large in number. Therefore, it's very clear that with a larger number of slots, better cooling of armature conductors can be easily achieved. Next important factor which is affecting the selection of number of armature slots is the flux pulsations. Basically, the flux pulsation is defined as the change in air gap flux due to the slottings. That is, due to the slotting, the air gap flux which will be present at the slot won't be same as that of the air gap flux which is present at the tooth. This change in air gap flux due to the effect of slotting is said to be flux pulsations. This flux pulsations gives rise to the problems of eddy current loss and magnetic noise. Both are actually unfavorable conditions. If the number of slots used in the machine are very large in number, then definitely the flux pulsations will be reduced, which further helps in the reduction of pole phase losses, that is eddy current losses, and the noise level of the machine. Consider the flux which is passing from this pole shoe to the armature through this 5 teeth that is shown here, 1, 2, 3, 4, 5. Now suppose if the armature is moved towards right by half slot pitch, as you will be able to see very clearly in this diagram, after moving the armature towards right side by half slot pitch. In this case, if you see, the flux is passing from the pole shoe towards the armature through this 6 teeth, 1, 2, 3, 4, 5, 6. Comparing this to in the aspect of reluctance, it can be seen very clearly that the reluctance in this case is greater than that of the reluctance in this position. This is because if you see in this case A, the number of teeth is only 5, whereas in the case of number B, after moving the armature by half slot pitch, the number of teeth which is coming under the influence of this pole shoe is 6. As the number of teeth are more in the case B, so definitely the reluctance over here will be less comparing with that of the reluctance in case A. As there occurs change in reluctance when this armature is rotating, that is while comparing this case A with case B, the armature is rotated towards right side by half slot pitch. So definitely while comparing these two cases, it's very clear that there is occurring a change in reluctance in these two cases. This further leads to the case of flux pulsations. Now consider the case of flux passing from the pole shoe to the armature through 5.5 teeth. You will be able to see very clearly 1, 2, 3, 4, 5, and half of the teeth is also included. Just like in the previous case, if the armature is made to rotate through half slot pitch, comparing this two, it's very clear that in this case the armature is rotated towards right side by half slot pitch. So now if you are seeing the flux which is passing from this pole shoe to the armature is 1, 2, 3, 4, 5 and half, that is 5.5. So it's very clear that in both these cases, that is even after the armature is rotated towards right side by half slot pitch, the flux which is passing from this pole shoe to the armature remains the same. That is, there is not occurring any flux pulsations as there is no change in the reluctance while comparing these two cases. So it's very clear that we can have the condition of no flux pulsations in air gap while the armature is rotating if we are choosing the number of slots under pole shoe to be a integer plus half value. See, in this case we have taken the number of slots under the pole shoe as an integer, that is 5, while in this case we have considered the number of slots under the pole shoe as 5.5, which is actually an integer plus half. So comparing with this case, there is not occurring any change in reluctance when the number of slots under the pole shoe is an integer plus half. As there is no change in the reluctance, definitely there won't occur any change in the flux, that is, there will not occur the flux pulsations. So it's clear that in order to avoid the flux pulsations and oscillations, the air gap reluctance per pair of poles should remain practically constant, and the air gap reluctance is made constant by choosing the values of number of slots under pole as an integer plus half. Next, while considering the cost factor, it is economical to choose a smaller number of slots. This is due to the fact that when the number of slots are small, definitely the charges for punching the slots also will be small. Next constraining factor is commutation. In order to achieve the condition for sparkless commutation, the flux pulsations under the interpole needs to be avoided. This can be easily avoided by increasing the number of slots. This leads to a constraining factor that the number of slots in the region between the tips of two adjacent poles should be at least 3. Next we are going to see the gate lines for selection of number of armature slots. The first gate line is the slot pitch should lie between 25 to 35 mm. Second is the slot loading should not exceed 1500 ampere. That is, the number of ampere conductors per slot should not exceed the value of 1500 ampere. Ampere conductors per slot is given by the relation IZ into ZS, where IZ is actually the current flowing through each of the conductor, and ZS is actually the total number of conductors which are present in a slot. So it must be taken care of that the value of IZ into ZS should not exceed 1500 ampere. As mentioned before, the number of slots per pole pair should be an odd integer in order to minimize the pulsation loss. We have clearly explained it by saying that the number of slots per pole shoe must be an integer plus half. Next is for the case of sparkless commutation, it must be ensured that the slots per pole should lie between 9 to 16. Another important point which must be noted that in the case of lap winding, the number of slots should be multiple of pole pair, whereas in the case of wave winding, the number of slots should not be the multiple of pole pair. So these are the gate lines which will affect the selection of number of armature slots. Next we are going to see the numerical problems associated with the selection of number of armature coils and armature slots. In this problem, first we are asked to determine the physical dimensions of the armature, that is diameter and length of armature core. It's given the armature drop, that is IARA drop in the machine is 4 volt. The ratio of pole arc to pole pitch is 0.7. And length of core, that is capital L, is 1.1 times the pole arc. Other than the physical dimensions, it is also asked to find the type of winding which we can use for this machine, and also we have to determine the number of armature conductors and number of slots in this machine. First, let's determine the values of capital D and capital L. For that, we have to use the output equation, that is PA is equal to C0 d square L into small n. PA is actually the power developed in the armature, and in this DC generator, the power developed in the armature is generated EMF into Ia into 10 raised to minus 3. As it is a shunt generator, the value of IL, that is the load current, can be easily determined by dividing the power with the voltage. Once after getting the value of load current, by adding it with the field current, in this problem the value of field current is 10 ampere, we will be able to determine the value of armature current, because in the case of a shunt generator, armature current is actually the sum of load current and field current. So in order to get the value of PA, we need to find the value of EG, that is actually this will be actually usually represented as EG. It is the voltage which is being induced in the armature. It can be easily determined from the terminal voltage and the voltage drop occurring in the armature, that is E is equal to V plus IARA. Once after determining the generated EMF and armature current, make the substitutions here and you can easily find the value of armature power developed, and it is found here as 58.14 kilowatt. Next we have to find the value of output coefficient. All these parameters are given directly in the problem. So make suitable substitutions and determine the value of C0. So once after knowing the values of PA and C0, the value of small n can be easily determined from the rated speed by dividing it with 60. So in this relation, now we know all the parameters except D and L. So we will be able to obtain a relation in D square L here, and that is 0.027. We need to find another relation in D and L in order to calculate the values of D and L separately. So the hint for that is given in the problem itself. That is, the length of core is about 1.1 times the pole arc. L is equal to 1.1 times B, and B is 70% of pole pitch. This pole pitch is actually pi d by P. So after making the substitution in this relation, we will be able to get a relation in L and D, that is L is equal to 0.6044 D. Solving these two relations, we can identify the values of D and L. So far we have determined the values of D and L. This we have already studied in our previous video sessions. Now let's see the portion of this problem which covers the topic of this current video session. We have to find which type of winding to be used for this problem. So in order to specify the winding, we will be considering the guidelines which we have chosen for the selection of number of poles. That is, the current per parallel path should not be more than 200 ampere and current per brush arm should not be more than 400 ampere. This is actually a basic rule in the case of armature winding. We have already calculated the value of armature current, and knowing the number of parallel paths, if we are considering it as a wave winding, it is actually 2. We will be able to determine the current per parallel path as 255 ampere, which is actually not a possible condition because we have very clearly studied that the current per parallel path should not exceed the value of 200 ampere. So definitely this machine can't have wave winding. That is, the armature winding cannot be of wave winding. Next we will see the condition of lap winding. So in the case of lap winding, the number of parallel paths is same as that of number of poles. In this problem, the number of poles is given as 4. So we can easily determine the current per parallel path by dividing the armature current with the number of poles. We will be getting it as 127.5, which is less than 200 ampere. Once after determining the current per parallel path, we can easily determine the current per brush arm by using the relation 2IA by P. The standard relation is 2IA by A, but in our case, as the number of parallel paths is same as that of number of poles, because we have finalized that we are going to proceed with lap winding, so from which we can determine the value of current per brush arm as 255 ampere, which is also satisfying the condition that the current per brush arm should be less than 400 ampere. So we have finally decided the winding which we are going to use for this machine is lap winding. Next it is asked to find the suitable value of number of armature conductors. It can be determined from the standard relation of generated EMF, that is 5P and Z by 60A. All these parameters are not mentioned in the problem. The values of capital E, small a, small n and small p are given. We have to identify the value of phi, then only we will be able to calculate the value of Z. The value of specific magnetic loading is given. You all very well know that the standard relation of specific magnetic loading is P phi divided by pi dl. So by using that relation we can easily determine the value of phi. Thereafter we have to substitute this value of phi in this relation to get the value of Z. So we have found out the value of number of armature conductors also. Next you are asked to find the value of number of slots. It's very clearly mentioned in the guidelines for selection of number of armature slots is that the slot pitch should lie between 25 to 35 mm. So by using that condition we will be able to identify that the values of number of slots lies between 32 and 45. As the winding we have considered is a lap winding, it's very clearly given in this last guideline that for lap winding number of slots should be multiple of pole pair. In our case the total number of poles is 4, therefore the number of pole pair will be 2. So we can eliminate all those values between 32 and 45 which are not actually multiples of 2. So after excluding all those values, finally we are left with only 32, 34, 36, 38, 40, 42 and 44. So among this one will be the actual number of slots. Next guideline is the slots per pole should lie between 9 to 16. In our case the number of poles is 4. So considering the minimum value of slots per pole, that is actually 9, we will be able to determine the number of armature slots will be starting from the value of 9 into 4, which is actually 36. Hence we can eliminate these two values. Considering that particular gate line, the number of slots will be 1 among the values from 36 to 44. that is 1 among 36, 38, 40, 42 and 44. Next we will see the very important gate line that is used to minimize the pulsation losses. Slots per pole pair should be a odd integer, or else we can say that slots per pole must be an integer plus half. So from 36 to 44, if we are dividing this 36 with the number of poles, what you will be getting is actually an integer. If you are dividing this 38 by number of poles, you will be able to get it as 9 plus half. As this particular value is in agreement with the gate line which we have just mentioned, that is the number of slots per pole must be an integer plus half, we can finally fix this as the actual number of armature slots which are required in this machine. That is, number of armature slots is equal to 38. This is a very important problem. We will see one more similar problem. A 4-pole 25 HP 500 volt 600 rpm series crane motor. It's actually a motor. In the previous case we have seen a generator. Its efficiency value is given. Pole faces are square and ratio of pole arc to pole pitch is given as 0.67. Assuming an average gap density of 0.55 Weber per meter square and ampere conductors per meter as 17,000, obtain the main dimensions of the core and particulars of a suitable armature winding. It's very clearly given that the pole face are square in shape. The pole faces are square in shape. That means L is equal to B. That is, the value of pole arc is same as that of the length of the machine, and the ratio B by tau is given as 0.67. Since it is being a square pole face, we can write L by tau is equal to 0.67, from which we will be able to obtain a relation in L and D, that is L is equal to 0.525 D. Then just like how we have determined another relation in D and L, that is D square L, by using the output equation, the same method is followed here also. So finally, after solving this two, we will be able to determine the values of D and L. Next, you are asked to find the particulars of a suitable armature winding. So first we have to specify the winding. So we will be first checking whether it's wave winding or lap winding. For that, first we will consider wave winding. In the case of wave winding, number of parallel paths is 2, whereas in the case of lap winding, the number of parallel paths is same as that of number of poles, that is actually 4 in this case. So while considering it as a wave winding, we will be able to identify the current which is flowing through the parallel path is 37.3 ampere, which is definitely, the current through the parallel path is 18.65, which is definitely less than 200 ampere. So we can fix that the winding which we will be using for this armature will be wave winding 1. Once after fixing that, in the next step we will be identifying the value of armature conductors. The value of armature conductors can be determined by using this relation, but the value of phi is not given directly in the problem. Indirectly, you are provided with the value of specific magnetic loading. As you know, the standard relation of specific magnetic loading is P phi divided by pi dl. So making suitable substitutions, you will be able to identify the value of phi, from which you can easily find the value of Z, and it is found to be 972 conductors. Next we are going to find or determine the value of number of armature slots. For that we will be seeing the gate line. The first gate line is the value of slot pitch has to lie between 25 and 35, from which we can say that the number of slots, armature slots values, lies between 30 and 42. As we have considered here is a wave winding, in the gate line it's very clearly mentioned for wave winding number of slots should not be a multiple of pole pair. That means it should not be multiple of 2, because the total number of poles is 4, so the number of pole pairs will be 2. So it's very clear that the number of armature slots should not be a multiple of 2. So you have to choose the values between 30 and 42, which are actually not the multiples of 2, and it is found to be 31, 33, 35, 37, 39 and 41. Now considering the gate line, the slot per pole should lie between 9 to 16 in order to prevent sparking. In the case of small machines, the value of 9 to 16, that particular range varies from 8 to 16. So between this 30 and 42, among the values 31, 33, 35, 37, 39 and 41, we have to consider the minimum value of slots per pole as 8. So in that case, the value can be between 32 to 16, therefore that is 64. So from this we can neglect this first term. Please be very careful with what I am saying now. Usually in the gate line it's very clearly mentioned that the range of slots per pole is lying between 9 to 16. But in the case of small machines, this range lies between 8 to 16. So in this problem we have considered a small machine, so definitely the value can be changed from 32 to 64. So we have to take those values which are common between 32 and 64 and 30 and 42. So we can easily neglect this 31. So what we are left with is 33, 35, 37, 39 and 41. In the case of wave winding, instead of taking the number of slots per pole as an integer plus half to reduce the flux pulsations, we will be considering the number of slots per pole arc to be an integer plus half in order to reduce the flux pulsations in the case of wave winding. But in the previous problem we have considered only number of slots per pole in order to reduce the flux pulsations, because here it was lap winding. In the case of wave winding, we will be considering slots per pole arc value to be an integer plus half in order to reduce the value of flux pulsations. So we will calculate the value of slots per pole arc by making the substitutions in this relation, and we will see which of them will be giving the value an integer plus half. So when we are seeing here, when the armature slot is 33 and when the armature slots is 39, we will be getting the slots per pole arc value is integer plus half, 5.5, 6.5. So it's clear that we must either choose this 33 or 39 from this range of slots. So please be very careful. This gate line is having a slight modification in the case of small machines. That is, the range is from 8 to 16 rather than 9 to 16. And another important thing which you must remember is, in the case of lap winding, what we will be considering is slots per pole. Its value has to be an integer plus half. Whereas in the case of wave winding, what we will be considering is slots per pole arc. Its value has to be an integer plus half. You must practice more problems from this. Then only you will be able to tackle the problem which will be asked for your university question. With that, we are completing the armature design of DC machines. Once in a university question paper, the theory portion of armature design has been asked for 8 marks or 10 marks. So in that case, you have to write the complete descriptions which we have studied in this session. Then only you will be able to get the full marks. Thank you.